Hi, for this section of Chapter 11, we're going to be talking about analysis of variance. Analysis of variance really has nothing to do with variances as a measure, but it actually is used to test whether there are significant differences in the means of more than two groups. You'll remember that when we had two different groups and we were measuring means, we used t-tests back in Chapter 10. But now we're looking at three or more groups. So analysis of variance has been used for quite a long time and usually used to be done by hand, but since we have PH-STAT and we have Excel, we are not going to do this by hand. So for these tests, either you have observational data, which means usually you did a survey and you gathered the data randomly and then you identified different groups and you tested analysis of variance. Or it can be experimental, meaning that you had control over the groups and you assigned workers or something, sales, something to some group, and usually in this case you can have equal sample sizes. So the mobile electronics data shown in figure 11.3 on page 353 has random samples of 5 selected sales in each of these 5 locations for sales. Anyway, so some terms that you need to be familiar with in this chapter. The term factor. Factor is the term for the groups, and they're always categorical in analysis of variance. So it could be, in this case, the different locations. It could be males and females. It could be sophomores, freshmen, sophomores, juniors, seniors. It could be just any kind of a categorical variable. This is sometimes called the independent variable, although we really don't use this term a whole lot until we get to regression a chapter or two over. The response variable, this is the numerical variable. This is what you're actually trying to measure. And so for our example of mobile electronics, what they're looking at is sales, the numerical variable, at these different locations where they've got these displays set up in their store. It's sometimes called the dependent variable, and those terms are a little bit confusing, but I'll explain further about those when we get over to the section on regression later this semester. Anyway, so and then treatment or the categories of the factor. We don't really use the word treatment so much, but that factor and response variable we do. There are some assumptions of analysis of variance that hold whether you're doing single factor analysis of variance or you're doing two-way analysis of variance. So these assumptions are that the response variable, that numerical one, is always normally distributed for each population group that you're testing. We usually assume this unless we have some sort of reason to believe that something different could be going on. And again, as we've seen in previous chapters, there are ways to test whether the samples are normally distributed, if you really have a question about this. The second assumption that we have is that when we took our sample, our observations were independent of each other. Again, this is part of your sampling design process, and you should, by taking a random sample, take care of this problem. And then the third one, which we do have to test for, is that the numerical variable, the response variable, the population variances for those groups are not significantly different from each other. This should always be tested as part of the analysis of variance procedure, and you use something called a Levine test for that. So today, this week, we're going to be looking at one-way analysis of variance, and we're going to do it all in Excel, although he's got all the stuff worked out in the book if you care to go back and look at the way to do that. So what we're going to do is we're going to go to Excel. I've already got the file open. It's a file saved on your on your Excel files, and you're going to open up the file called Mobile Electronics, and you should see something that looks like what I have here. So there are 4 locations in the store, either in aisle, in the front of the store, at a kiosk, or an expert. I'm not sure what that means exactly, but move that over a little bit. And anyway, so to run our analysis of variance is really simple. In PHDAT, it's already open. You go to multiple sample test. You pick off Way ANOVA, and you say okay, and it pops up with a dialog box. The first thing it wants to know is the level of significance. We're going to assume it's 0.05. That's our alpha level, unless you're told something different in a problem. And then the group data cell range. This is the block of cells that contain our actual data. So there it is. I have 5 observations from each of the 4 locations, and the first cells do contain labels. And then you want to make sure this box, I think it pops up automatically, but make sure this box that says Tukey-Kramer procedure is selected. This will give you your pairwise comparisons, which we'll talk about in just a few minutes. And you say okay. And when you say okay, it pops up with this thing saying you have to look up a Q statistic and enter that value in cell B15. And all you can do at this point is to say okay, and everything happens, and it highlights cell B15 right here on the sheet. So to look this statistic up, you go to the studentized range table in your book on page 650, look at the 0.05 table. The numerator, degrees of freedom, equals C, which is the number of groups. So you're going to look in the column that says 4, and the denominator, degrees of freedom, is your total sample size, N, minus C, the number of groups. In our case, we had a total sample size of 20 minus 4 gives us 16. And the intersections of the column 4 and row with 16 is the value 4.05. So you just basically type that in and press enter on the computer, and everything pops up. It does all the analysis. So that's how you get your analysis there. And you will see that you've got your ANOVA run and you've got your Tukey-Kramer run. Anyway, back to my little handout here. Here's my single factor. I just copied it over onto the sheet in Word. So here is the output for my ANOVA. The thing that you are most interested in for this first hypothesis test of differences in the means is the p-value located in this ANOVA table. Stands for analysis of variance. And you'll see that you can go back and look in the book. They explain how all these numbers come about. But here's your p-value. It's 0.0000. And this test is an overall test. It's the first thing you do, and it is to determine whether there are significant differences in the means between the groups. It does not tell you which groups are different from the others, just that something's different. So when you write your hypotheses for these, you should write your null hypothesis as mu1 equals mu2 equals mu3 equals mu4, meaning they're all equal to each other. And the alternate hypothesis, the H1, should say not all of them are equal. This gives you some wiggle room because you may have a situation where 2 groups are different from each other, but the others are not, and you're just looking for differences, period. Your decision in this case would be to reject your HO because your p-value, and in the ANOVA table it's listed as 0.0000, so you're going to write that as less than 0.000 and put a 1 at that last decimal place shown. So since your p-value is less than 0.0001, you would reject the null hypothesis because, again, our alpha level was 0.05. It's less than that. And then note that there's an ANOVA table on page 353 in your book that explains how these numbers fit together numerically. Remember that C, again, equals the number of factors, groups, and N equals the total sample size. And you can go through and figure exactly how all these numbers were created on the table. So that's the first part. We've now identified that there are differences between our groups. The second thing we want to do then is we want to figure out which groups are different than the others. This is our second test. So for this we use our Tukey-Kramer multiple comparisons data that we already figured out. Once we put in the 4.05 and pressed enter, it gave us our result. So the hypothesis to determine which groups are different have to be written out individually. In our case, we have 4 different groups, so we have 6 different sets of hypotheses. You look at each pair. The order doesn't matter. So if you said mu1 is equal to mu2, that's the same thing as saying mu2 is equal to mu1. So you just need each different set of pairs. So all the hypotheses are here. Your result is up here under results in this column, and you can see that the means are different for all the groups except group 1 to 4. Groups 1 and 4 are not different from each other. Now, you're going to have to explain this to your boss. He wants to know what this tells him. Well, what you could explain, and I like pictures better than anything else, but if I was explaining this, I would say that group 2 is different from everything else, group 3 is different from everything else, and then groups 1 and 4 are not significantly different from each other. So you could go back and you could look, and probably his next question is going to be which group is the best. And I would go back and look at my data, and here's your average sales up here in the Tukey-Kramer, and you'll see that the front had an average sales of 31.994. The kiosk had average sales of 30.912. Those were different from each other, and they were different from 1 and 4. But the difference between the in-aisle sales and the expert sales is not significantly different at 0.05. So if your boss said, you know, which one should I pick? I would probably tell him pick front location. If he said, is it worth paying somebody, an expert, and having it set up there versus an in-aisle display, I would say no, because those are not significantly different from each other. So anyway, you just have to interpret it. And I like pictures, but you may not. Anyway, so then the next thing you want to do is, the one thing we can test about our assumptions is equality of variances. For this, you do the Levene test. So the way to do the Levene test, you go back to Excel, back to my file, and back to my data tab, where my initial data was. Go to multiple sample test and pick the Levene test. It's listed there. And you get a table, a dialog box that looks very much like the one you got for analysis of variance. Pick off the location of all your sample data and make sure first cells contains labels is checked, and there's nothing else to check on this. Just say okay, and you're going to add a whole bunch of sheets, and here's your Levene output here. I copied this over into Word, so here it is. This is one where it looks very much like the hypothesis for the overall test. I should have an equals out here. Sorry, let me go ahead and put this in while I see it. So I find my sigma up here. I can't find anything up here. Sigma squared. This is group 4. And then not all sigma squared are equal. So again, it's written in very much the same format. And the p-value, again, in the ANOVA table up here, it's 0.3953, is much greater than 0.05, which is our alpha level. So our decision is not to reject our HO, since this 0.3953 is greater than 0.05. And this means that there's no significant differences in the variances of the sample groups that we have. And we're going to then assume that that means there's no difference in the populations. So as long as our decision is do not reject here, then this means we haven't violated our assumption. Anyway, that's part 1, single factor analysis of variance. I will get the other one up later this week. Thank you.